Good morning, students. Today we are going to discuss about electromagnetic induction and alternative current. Previous lesson we discussed magnetic field, magnetism and magnetic effect of current. So in previous lessons we are consider when the current passing through the coil, the current carrying coil act as a magnet. The current carrying coil act as a magnet. So the magnet means it contains magnetic lines of forces. The magnetic lines of forces. The magnet means it contains magnetic lines of forces. So in this lesson we're going to learn how it is the current producing a magnetic field. So in this lesson particularly we're going to find that magnetic field producing the electric current, the current producing a magnetic field. Similarly in this lesson the electromagnetic induction and alternative current. In this lesson we're going to learn the magnetic field producing electric current. It's a reverse type. Okay, when the current passing through the coil it's producing magnetic field. In this lesson we're going to discuss the magnetic field passing through the coil. So here we are taking a one bar magnet. So this is a magnetic lines of forces north pole to south pole. So when we placing one coil, this is a solenoid. So when we placed one coil in this magnetic field, so when the magnetic field lines linked with the coil, it produces the electric current. So in previous lesson we discussed the current when it is passed through the coil, the current carrying coil act as a magnet. So in this lesson it's a reverse of this. When the lines of forces passing through the coil, it's producing the current. This is called as the electromagnetic induction. Next one, magnetic flux. So we know that magnetic flux means what? So when we're taking a one magnet, the magnetic contain magnetic lines of forces. We are taking a one unit area in this magnetic field. The number of magnetic field passing through the unit area, it's called as the magnetic flux. So in this magnetic field we are taking a one unit area. The number of field lines, the number of magnetic field lines passing through the unit area, it's called as the magnetic flux. So we can write the flux formula pi, it's equal to BA. So dear students, now we are going to discuss about Faraday's experiment. So Faraday's found that when the when the magnetic field lines connect with the copper coil, it's producing the electric field. So here we are taking a one copper coil. So the copper coil is nothing but what? We are taking a solenoid. So this is a copper coil. It's called as the solenoid. So when it is a twist, is rotate itself, it's called as the what? It's a solenoid. So we are taking a one bar magnet. So bar magnet containing what? It's a magnetic field lines around it. Okay, so here in a first diagram, this is a first diagram. This diagram shows the bar magnet in a no motion. Okay, so here there is a no motion, the bar magnet in a rest, and also copper coil also present in a rest. So at this time, so there is a no current produced in it, so the galvanometer shows in a 0. So it means there is a no current produced in it, that is a induced current. There is a no current produced in it when the bar magnet in a rest. Similarly the copper coil in a rest. So this is the second diagram. So the magnet moves towards the left side. So it moves now towards the left side. So that when it is moves towards the left side means the magnetic field lines connected with the copper coil. When it is moves left side means what will happen? The magnetic field lines connected with the copper coil. When the magnetic field lines connected with the copper coil means it's producing what? induced current. Whenever the magnetic field lines connected with the copper coil, it's producing the electric field. So the galvanometer which is get deflection. So when it is moves left side means the induced current passing through that opposite direction towards the magnetic passing through the conductor. So this is induced EMF. The galvanometer shows deflection. This is called as the what is a induced EMF. So this is a third diagram. So here the magnet present inside of the copper coil. So both are in rest only. The copper coil and magnet both are in a rest only. So at the time the galvanometer shows no deflection. The galvanometer shows no deflection. So it states it gives the result there is a no induced EMF produced in this copper coil. There is a no current produced in the copper coil. So next diagram, the magnet moves away from that copper coil. So here that galvanometer deflection shows opposite direction. So this is states that the copper coil, that magnet moves away from that copper coil means the induced EMF direction towards opposite to the direction. So here the induced EMF direction is what? The current producing direction, the current passing direction is another side. So this is called as the what? This is the induced EMF. It's producing another side. When it is magnet moves opposite side away from the coil means the current producing direction towards like this. So the galvanometer shows current passing direction. In this diagram, the higher speed, the magnet is moves a higher speed, so that the field lines are linking with the copper coil. It's a maximum. So its induced EMF producing EMF is its a maximum. It shows the maximum deflection. It states that when the magnet moves high speed means the producing current also increased. In this diagram, we are changing the polarity of the magnet. So the south pole of the magnet we have to linked with the copper coil. So the deflection, so when we move towards the copper coil means in a previous case the deflection in a right side, but now the deflection is the left side because we are changing the polarity of the magnetic field. So the producing current direction towards opposite direction. Faraday's second experiment. So increasing current. So we are using a one electromagnet when the current is passing through the coil. So we know that current carrying a coil act as a magnet. So here we are increasing the passing current. The magnetic field will be increasing. So this is a Faraday's second experiment. So it's a normal when the current carrying a conductor act as a magnet. So the magnetic field lines linked with the copper coil, it's producing the deflection. So it states that its deflection shows that the induced EMF, the current is produced in that copper coil. So this is implies that whenever the field lines linked with the copper coil, it's producing the deflection. So when we open the circuit, the magnetic field will be decreased automatically. The deflection also slightly decreased. The producing current also slightly decreased. So this is Faraday's second experiment. So now we're going to discuss the conclusion of this experiment. So that is called as the Faraday's laws of electromagnetic induction. So from the experiment we can conclude the conclusions of Faraday's experiments or states two laws, first law and second law. Faraday's first law states that whenever magnetic flux linked with the closed circuit changes, an EMF is induced in the circuit. Whenever magnetic flux linked with the closed circuit changes, an EMF induced in the circuit. Second law, the magnitude of induced EMF in a closed circuit is equal to the time rate of change of magnetic flux linked with the circuit. The magnitude of induced EMF in a closed circuit is equal to the time rate of change of magnetic flux linked with the circuit. The equation shows the EMF psi, it's equal to the rate of change of flux minus d pi by dt. So now we're going to discuss Fleming's right hand rule. stretch your right hand, the forefinger, middle finger, and thumb finger mutually perpendicular. So when we stretch like this, so that forefinger and middle finger and thumb finger stretch mutually perpendicular. So in this, that forefinger indicates that forefinger indicates that the direction of the magnetic field, and the thumb finger indicates that the direction of the conductor, and middle finger indicates that induced current direction. So this is a very important rule, Fleming's right hand rule. Fleming's right hand rule states that stretch your forefinger, middle finger, and thumb finger mutually perpendicular. The forefinger indicates the direction of the magnetic field, and the middle finger indicates that the direction of the induced current, and the extend thumb indicates that direction of motion of the conductor. Dear students, now we're going to see next topic, eddy current. Normally, when the magnetic lines of forces, this is the north pole, this is south pole, the magnet containing a magnetic lines of forces, when the lines of forces linked with a coil, it's producing the induced EMF. So we learn that, so when the lines of forces linked with the coil, it's producing the induced EMF. So now we are taking this metal in a sheet form or in a solid form. So when this is a current carrying a conductor, current carrying conductor act as a magnet. The lines of forces linked with the sheet or solid metal shaped conductor, the current, induced current, is created in the form of circular, because there is a no way to go here and there. So the induced current created in the circular form, this is this circular form induced current is called as the eddy current. So simply, that magnetic lines of forces linked with the sheet, metal sheet, there is a no way to move induced current, so that induced current is formed as a circular. So this is called as the what? This circular shaped induced current is called as the eddy current. Uses of eddy current. So one of the uses of eddy current is nothing but induction stove. So in this induction stove, inside they are fixed to one copper coil. When the current is passed through the copper coil, the powerful magnetic field will be produced. The magnetic field which is connected with the suitable vessel. So we are using a one cooking vessel. The magnetic field linked with the in this cooking vessel, it's producing that induced EMF. Its shape is what? It's producing that circular shape. So this is creating the vessel producing that circular shape induced current. This is called as the what? Eddy current. Due to this eddy current, the Joule's law of heating is produced, so that the food is cooked. So here we can easily understand, the inside the induction stove, the copper coil is present, the powerful copper coil is present. When the current is passed through the copper coil, so the when the current is passed through the copper coil, the current carrying copper coil act as a magnet. So when that magnetic field is a high frequency alternative magnetic field, so when that magnetic field linked with the cooking pan, so it's creating that induced current in a circular shape. The circular shaped induced current is called as the eddy current. So the induction stove is one of the applications of the eddy current. So next use is eddy current brake. This is a eddy current braking system, is generally used in speed trains and roller coasters. So we can see this diagram. So this is the electromagnet. So when the electromagnet is switched on, the magnetic field contacted with the metal sheet, the metal tire, and it's producing the electric current. It's a induced current, that is in a circular shaped induced current, that is called as the what? It's a eddy current. So when that electromagnet is turned on, the magnetic field linked with the metal and it's producing that eddy current. That eddy current opposes the wheel rotation, so this is called as the what? Eddy current brake. So we can see here the circular shape eddy current. So the circular shape brake. So when the electromagnet is magnetic field is contacted with the circular shape metal, so which is opposes that rotation of the wheel. Next application is eddy current testing. So we are taking a one metal plate. So when the magnetic field passed through the metal plate, the eddy current will be produced. So somewhere some defects is there, means the eddy current amplitude will be changed. So now we can easily understand some more defects are present in this metal. So because some eddy current amplitude will be changed, means we can able to easily understand some defects is present in this metal. So likewise the eddy currents are used in testing purposes. So now we're going to discuss self-induction. Self-induction means is nothing but the flux linkage of the coil. The flux linkage of the coil, it's called as the self-induction. So here we're going to calculate what is the self-induction of a long solenoid. So this is a long solenoid. This is a copper coil. The twist of this copper coil, it's called as the solenoid. Okay, so here the self induction of a long solenoid, we're going to find what is the self induction of a long solenoid. So here the magnetic field, when the current is passed through the solenoid, it acts as a magnet. So the magnetic field present in is nothing but what? It's a B magnetic field, which is equal to mu naught Ni. So mu naught is the permittivity and N is the number of turns and I is the passing current through the coil. So this is the passing current through the coil. So here the magnetic field B, which is equal to mu naught Ni. The flux linkage of the coil is what? The flux linkage of the coil is nothing but pi B. Pi B, which is equal to B dA vector. So A is nothing but area of the cross section. So the flux linkage is nothing but B vector dA vector. Integration of B vector dA vector is nothing but what? It's a flux. Pi, it's equal to integration B vector dA vector. So when we integrate, this integration symbol will be removed. This is when we integrate, the differentiation will be removed. So we are getting a BA. So when we remove this vector quantity, we have to introduce one scalar, that is a cos theta. So when we remove this vector term, so we have to introduce one constant, that is a cos theta. Integration of dA, it gives us a BA cos theta. So here the theta value is nothing but there is a no angle present in it. The theta angle is nothing but what? 0 degree. So cos 0. So cos 0 is nothing but what? It's a 1. So cos 0 is nothing but 1. So the flux pi b, which is equal to BA. So we are getting a flux pi b, which is equal to BA. So we know that B value we already calculated. So B value is nothing but what? Mu naught Ni. So B value is nothing but mu naught Ni. We have to substitute in this B value. So we have to substitute in this mu naught Ni into A. We are getting a pi B value mu naught Ni into A. So here the total number of turns is nothing but what? The number of twist. One twist is nothing but is a N. The number of twist into length, overall length. When we multiply the length of the coil and number of twists, it gives us a total number of twists. The N is equal to NL. So now we going to find a multiply by this N. So when we multiply with this N, means we are getting a N pi B. So when we multiply this with the N, means it gives us N pi B. The NL multiplication, which gives us NL mu naught NIA. So this N pi B, the number of turns into flux, it gives us what is N pi B. So it's nothing but Li. So n pi b it is equal to Li. L states that self induction. So n pi b which is equal to Li. So now we can substitute in this n pi b instead of this Li. N pi b, for this we have to substitute Li because n pi b which is equal to Li. So when we substitute, we are getting what from this equation? Li which is equal to mu naught n square Al. So we have to cancel. So I we have to cancel. We are getting self induction of the long solenoid is nothing but L, which is equal to mu naught n square Al. This is the self induction of the long solenoid.